Hi everyone, welcome to CS 188 section 7, and today I'll go over the solutions for the worksheet. So the first problem is on Bayes nets. In a parallel universe, the Green Party is running for the presidency. Whether a Green Party president is elected, G, will have an effect on whether marijuana is legalized, M, which then influences whether the budget is balanced, B, and whether class attendance increases, C. Under their power probability, the analysts model the situation with the Bayes net below. So here we have the Bayes net and the local conditional probability tables. So the full joint is given below, fill in the missing values. So for this problem, what we're going to have to do is multiply. The full joint probability is represented by multiplying the local conditional probabilities. So what we have is the probability of G, M, B, C equals the probability of G times the probability of M given G times the probability of B given M times the probability of C given M. So that's how we're actually going to calculate all these values. So what's the probability of plus G? It's going to be 1 over 10. Probability of plus M given plus G is 2 over 3. Probability of plus B given plus M is 4 over 10. And probability of minus C given plus M is 3 over 4. So you can multiply those out to get the probability. Let's keep moving on. So probability of plus G is again 1 over 10. Plus M given plus G is 2 over 3. Minus B given plus M is 6 over 10. And minus C given plus M is 3 over 4. Cool. So let's keep going. Plus G is has a probability of 110. Minus M given plus G is 1 over 3. Minus B given minus M is 8 over 10. And plus C given minus M is 1/2. Probability of minus G is 9 over 10. Plus M given minus G is 1 over 4. Plus B given plus M is 4 over 10. And plus C given plus M is 1 over 4. So probability of minus G is again 9 over 10. Plus M given minus G is again 1 over 4. Minus B given plus M is 6 over 10. And plus C given plus M is 1 over 4. And for the last one, minus G is 9 over 10. Minus M given minus G is 3 over 4. Minus B given minus M is 8 over 10. And plus C given minus M is 1/2. Cool. So now we've filled in the table. Okay, so now let's look at the second problem, which is on variable elimination. So what they ask us to do is that using the Bayes net, which is shown right here, we want to compute probability of y given plus z. All the variables have binary domains, and they're giving us the variable elimination ordering. So how to choose the hidden variables. So x, t, u, v, w. So complete the following descriptions of the factors generated during variable elimination. So at the very start, we have the following factors, which are all the local conditional probability tables. question A. When eliminating x, we generate a new factor f1, which leaves us with factors blank. So first, we need to generate the factor f1, which, because we're eliminating x, we need to look at every factor that involves x. So I'm going to underline them. I've seen x, x, and we just have 2 right there. So my new factor, f1, is going to be a function of all of the underlying factors and the variables that are not x. So I'm going to have t and plus z. So that equals, I'm going to sum out over x, the probability of x given t, and probability of plus z given x. And now I need to write the remaining factors, which is everything that's not underlined and my new factor. So probability of t, probability of u given t, probability of v given t, probability of w given t, probability of y given v comma w, and this new factor f1 of t comma plus z. Cool. So now we eliminate t. So let's underline everything that involves a t, which is everything except this one. So now we create a new factor f2 of a function of everything else except t in the underlying factors. So we have a u, we have a v, we have a w, we have a plus z. And that equals the sum over all t values of the product of all the underlying factors. Probability of t, probability of u given t, probability of v given t, probability of w given t, and sorry, ran out of room. So on the next line, continuation f1 of t comma plus z. So now what factors do I have left? I have probability of y given v, and let me reset. Probability of y given v comma w, and this new factor f2. So notice that my old factor is actually gone because we joined it. So now we just only have f2. Now we eliminate u. So what factors involve u? Well, it's actually only this one. So we get f3. It's function of v comma w comma plus z equals the sum over u of, this one's fairly easy since there's only one factor, comma v comma w comma plus z. Now I'm left with the factors probability of y given v comma w and f3 of v comma w comma plus z. Now we want to eliminate v. So what involves v? Well, actually both of the factors do. So now I can create a factor f4, which is a function of the remaining variables. So we have a y, we'll have a w, we'll have a plus z. And what does this equal? We sum out over v of the joining of factors, so multiplying them together. And f3 of little v, w, plus c. So now what do we have left? Well, we only have factor f4 of y comma w comma plus z. And now we eliminate w. There's only one factor and it does involve w. So we get f5 of y comma plus z equals the sum over w of f4 of y comma w comma plus z. And that just leaves us with the factor f5 of y comma c. Cool. Okay, so now we've actually done variable elimination. And now they're asking us, how do you obtain probability of y given plus z from the factors left above? So let's consider probability of y given plus c. Let's actually rewrite it using Bayes' rule. This might help us think a little bit. So probability of y given plus z over probability of plus c. Okay, so let's look at this. And let's actually look at the bottom. What is the probability of plus c? Well, actually, we don't know, but we know this is a number. So some scalar value. And we know this is a probability. And we also know that because it's a probability, it must sum to 1. So all we actually really need to find out is something, this top, the probability of y comma plus c, something that's proportional to it. Well, we actually have that. So the probability of y comma plus z is actually proportional to our f5 of y comma plus c. And why is this true? Well, f5 is obtained from taking our full joint probability when we multiplied everything together. So this multiplied together is our full joint. And we were summing out over the hidden variables, but we weren't normalizing. So now f5 is some unnormalized version of the joint over y and plus c. So all we actually have to do is probability of y given plus z equals f5 y comma plus z over, so we make it equal and then we normalize to sum to 1. So that's a valid probability distribution. Okay, so now for G, what is the size of the largest factor that gets generated during the process above? So let's look at all the factors during all the iterations of variable elimination and find the one with the most variables. So if we start at the top, here we see we have a factor of size 3. And in part A, we still, size 3 is the biggest. In part B, size 3 is still the biggest. The plus z doesn't count because it's a fixed value. And we have plus 3 here, plus 2, plus 1. So the size of the largest factor is actually f2 of u comma v comma w comma plus z. And because it's binary, the size is 2 to the 3. So now for question H, does there exist a better elimination ordering, one which generates smaller factors? So let's take a look at our graph right here. So I'm going to give one example of an ordering that generates smaller size factors, but in general there could actually be multiple orderings. So first, in general, we like to look at nodes that have few arrows involved with them, and in general leaves are also a good place to start. So let's start with, we're going to choose X. So I'm going to keep track of our order actually up here, since we want to look at the graph while we're doing this. So if X is first, then what factor will I get out of it? Well, I'll get a factor that involves t and x. So we can write this out explicitly. So it involves probability of x given t and probability of z plus z given x. So that'll give us a factor, an arrow, that only involves t and plus c. Alright, cool. So that actually didn't generate a big factor. So that generated a factor of size 1. So I'll keep track of the size that it generates. Okay. So we did this for x. So by symmetry, we can actually do this for u also. So we do it for u, then we would also generate a factor of size 1. Now, let's look through. Okay, so we're going to have t, this middle part is what's left. So we can actually start at the top, and if we choose t, the only variables involved are v and w, and they'll be combined. So we'll actually make a factor of size 2. Now we can choose v or w, it doesn't matter. And after that, it would generate a factor of size 2. So these are 1, but then y is also included, so it'll be y and w, so factor size 2. And then I can eliminate w, and that'll just give me a factor of size 1 because only y will be left. So now we found an ordering x, u, t, v, w. Which generates on the largest size of 2 squared, which is better. Yeah, a good task is actually try finding some other orderings which also give a small factor.